You can watch this and other programs online at booktv.org.
Physicist Freeman Dyson is next on Book TV. He talks about his book of essays, Dreams of Earth and Sky, in which he writes about global warming, biotechnology, and more.
Good evening, everyone. Thank you very much for coming. Just the usual reminders before we begin. Thank you for that. Please silence your cell phones. Please refrain from taking flash photography. And then also please plan to join us upstairs afterward for the book signing. And in case you weren't aware, we podcast most of these events. There are more than 1,300 podcasts up there for you to listen to. Tell your grandchildren. There are a lot of classics up there, too, and your kids. They can get some homework done pretty quickly that way. My name is Andy Cahan, Director of Author Events, and I'm very pleased to welcome you as well as our guests this evening. Freeman Dyson is an iconoclast, a genius, and one of the great minds in physics, mathematics, and popular science. Everything else that you need to know before he takes the stage is either in his books or in the programs in your laps. Tonight, since we only have 60 minutes of Mr. Dyson's time, 59, it would be a waste of vital nitrogen and seconds to tell you any more than to say that Mr. Dyson will be interviewed by Dave Goldberg, Professor of Physics at Drexel University and the author of The Universe in the Rearview Mirror. Please welcome to the Free Library of Philadelphia, Freeman Dyson and Dave Goldberg.
So welcome to everyone. Welcome to Freeman Dyson. I'd like to begin by talking about the title of your latest book, which you borrowed from the Soviet rocket scientist Konstantin Tsiolkovsky. If you would, tell us a little bit about Tsiolkovsky's book, and in particular, whether you consider your own to be in some sense a tribute to his vision of space travel.
Yeah, no, the great thing about Tsiolkovsky was that he was really interested in biology more than in engineering. So although he actually worked out rocket equations and understood how to do the engineering part, but he understood that if you really want to go into space seriously, it's much more a problem of biology than a problem of engineering. It's not just getting into space, it's what do you do when you get there.
So on that topic, you make a statement, a very interesting claim early in your book. You say the last century, the 20th century, is the century of physics. This one, you say, is the century of biology. I was speculating that perhaps the 18th century or the 19th century is the century of chemistry. And on that topic, sort of thinking from the biological perspective, you make a very interesting comment with regards to our understanding of biology. And so if I can quote a little bit, you talk about evolution, and you make a very provocative claim. If I can quote, "The Darwinian interlude has lasted for about 2 or 3 billion years. Now, after 3 billion years, the Darwinian interlude is over. A single species, Homo sapien, begins to dominate and reorganize the biosphere. Since that time, cultural evolution has replaced biological evolution as the main driving force of change." So, this is a big question, but I think you're up to it. I was hoping you might be able to tell us how, in your opinion, human beings have changed the nature of evolution. I'd also, as a side note, be very interested in hearing how the biologists have responded to your claim.
Yeah, well, I learned a lot recently from Peter and Rosemary Grant, who are biologists who worked in the Galapagos Islands. And they spent 20 years, in fact, living on one island in the Galapagos, and they got to know every bird that is there personally and could understand the inheritance of characteristics, particularly the beaks, from one generation to the next. And their main conclusion, which came really as a big surprise to them and to us, is that evolution goes very fast. This is quite contrary to what Darwin imagined. Of course, Darwin also visited the Galapagos, but he didn't stay there long enough actually to see evolution happening. But the Grants did. And it's quite remarkable how quickly these species of finches, which Darwin observed, actually do evolve from year to year and from decade to decade. So you don't, Darwin, of course, started out life as a geologist, not as a biologist. So he always tended to think in geological terms. Everything had to be slow. So he had the notion that evolution was always millions of years. But in reality, that's not true. And as the Grants discovered in a very practical way, you can, in fact, evolve species, and this is natural selection. This is nothing artificial. They're observing the variation of the finches from year to year essentially because these islands have very rapid and quite abrupt fluctuations of climate. One year will be wet and the next year will be dry. And that makes a big difference to the birds. It means either food is abundant or scarce. And what happens is that natural selection operates on that kind of rapid time scale. So it is actually not true that cultural evolution is necessarily faster than biological evolution. Both kinds actually go fast.
So, sort of follow up on that, because one of the things that sort of struck me, I mean, so you would now say that it's more of a mix of the two, that Darwin's day is not necessarily over.
No, of course it's not over. I mean, that was, of course, an exaggeration. But it is true that human domination is a fact, that we are in control of the biosphere to a great extent. It's up to us not to mess it up.
So, at the risk of sort of drawing my knowledge of the biological world from movies, I mean, one of the lessons we often learn is that we underestimate the microscopic world. So we engineer, individual plants. We engineer large animals. We carve out large swaths of farmland and things like that. But there's a lot going on beyond our control, beyond our everyday interpretation. So back at the bacterial level, even ants and things like that. Do we miss basically the microscopic world because we have so clearly dominated the world on the macroscopic scale?
Well, no, I wouldn't say that. After all, a very large amount of biology is concerned with microbes. In fact, most of what we learned about fundamental biology comes from studying microbes and viruses in particular. So I think we are having at least as big an effect on the microbial world as we have on the big animals. In both cases, we don't control it, but we are certainly disturbing it very seriously.
So this brings up an important point. So you are a physicist. Well, you are a physicist among many, many other things. As a student, I knew your work in the context of your contributions to quantum mechanics and quantum field theory in particular. But I think it's fair now to call you a polymath, and your contributions are fairly extensive. But this particular book, for those of you who haven't read it yet, it's a collection primarily of essays and book reviews. And one of the remarkable things is how much ground it covers. So we've already discussed a little bit about biology, there's discussions of physics, history, and so on. Can you describe a bit your process of diving into a new field, biology, ecology, evolution, economics, so on? Just if you could describe your process, describe what you learn, and if it's not too much, maybe your sense of like how daunting it can be to go into a world where other people have generated expertise and to develop that expertise yourself.
Well, I would say that I'm only following the sort of normal development of getting old, that as you get old, you get broader and broader and shallower. like a river reaching the ocean. And anyhow, and of course, writing books is a congenial activity for an old gentleman. It can be done in your own time. And I've had enormous advantage of living in a community at the Institute for Advanced Study at Princeton, which is full of bright young people. So I have opportunity to get to know people. I think that's why I find it easy to get interested in a lot of different subjects, just because I get to know a lot of very exciting people, and I have this wonderful situation of being a member of the club where most of the other members are 70 years younger.
So, I mean, so of course, one of the exciting things for me interviewing today is I've known you as a thinker for a number of years. I met you actually when I was a student, very briefly. But in your book, you write about some of your heroes. You write very lovingly, in particular, about Richard Feynman in a chapter devoted to 2 biographies of him. But you begin the chapter with a very general discussion of sort of a scientist, the scientist with a capital S perhaps, as personality. And you put Einstein and Stephen Hawking in one side, one category, and people like Richard Dawkins and Neil deGrasse Tyson and Carl Sagan on the other. To me, Feynman comes across as sort of a scientific hero to you. And I'll add, just as a side note, he's one of my own as well. But I'd like to hear what sort of draws you to him as a thinker, and why. I mean, there are so many important physicists in the 20th century. Why the reputation, the enduring reputation of Feynman as a physicist hero to so many young students even now?
Yeah, well, it was an enormous piece of luck, of course. I came from England to this country and was a graduate student at Cornell. And I came to Cornell to work with Hans Bethe, which was already, of course, a tremendous piece of luck. But what was even more amazing was this young guy, Feynman, whom I had never heard of, who was right there. And I got to know him in the first week and immediately understood this was a genius. And I couldn't have been luckier. He was not only a genius, but also a clown, and he enjoyed performing. And I only had to sit and listen while he chatted away about all kinds of things. So it was just obvious that he was an enormous opportunity for me just to get to know him and to learn from him all the things he knew, which was a lot. And it turned out, of course, that he was in the process then of understanding quantum mechanics in a new way, which nobody else understood, and which was quite different from everybody else. Everybody else in theoretical physics used to write down an equation and then solve it. And that was the normal way of doing science. And, well, with Feynman, it wasn't like that. With Feynman, you just wrote down the solution, but you never wrote down the equation.
So,
and he did that by drawing pictures. And so I had to, it was just astonishing how well this worked. He got all the right answers and nobody understood why. So I made that my task, just to understand Feynman and explain him to other people. That's what I did.
So that's so one of the I actually thought it was very interesting when I contrasted your essay on Feynman to your piece on Paul Dirac. So Paul Dirac was enormously influential in our understanding of the unification, well, of quantum mechanics generally, but also the unification of quantum mechanics and Einstein's theory of special relativity. But I mean, they're just too numerous to list. And yet, Dirac doesn't have this sort of enduring mythos around him in the way that Feynman does, and yet his contributions are among the most important in the 20th century. And I was wondering, sort of using your piece as a launching point, if you could comment on why that is.
Yeah, I think the answer is very simple, that Feynman just enjoyed a crowd. He loved to play up to the public. He liked to fool around, and that, of course, was quite the opposite of Dirac. Dirac always spoke as few words as possible, and if he was asked a question, he would usually answer yes or no, and that was it. So it was quite normal that the public would respond to Feynman because Feynman responded to the public, and so that to me was quite a surprise. I mean, I knew Feynman, of course, as a scientist and also as a friend, but I did not think of him as a public figure in those days. And what I think is wonderful is the public really does have good taste. The public understood how great he is, and that did come as a surprise. Just yesterday, I wrote another book review, which went off yesterday, on Max Planck, who was a great physicist, contemporary of Einstein, and they were very close friends. And you had there the same contrast, that Einstein, of course, was a great physicist. Everybody knows about him. Planck was really equally great as a scientist. Planck was the father of quantum mechanics. He was an enormously powerful scientist and an admirable human being in all sorts of ways. But he was like Dirac. He kept quiet. So everybody admires Einstein. Very few people admire Planck. And the reason is exactly the same, that Planck wasn't happy in front of the microphone. Einstein was.
So to turn it around on you a little bit, so you have this lengthy career. You've written all of these books. How do you see your own role in sort of the pantheon of a scientist as a personality?
Oh, well, you never know, of course, what you'll end up being famous for. And I don't, the main thing is I don't take myself too seriously. I've always had a short attention span. I love to jump around from one thing to another and enjoy life. And so I've been happy to have a big family, to have many friends, and to have some interesting work. But they are in that order of importance. Family first, friends second, work third, which is why I'm not really a world-class scientist. I'm just a human being who happens to be good at a particular trade.
No comment on that. You are at very least an observer of not just physics, but all sciences. But I'm curious, as somebody a little older than I'd like, but certainly early enough in my career where there's opportunities to tackle new problems. I'm curious what you think are the biggest remaining problems in physics, the biggest questions in physics.
Well, I, of course, talk mostly to astronomers and not so much to particle physicists and other kinds of physicists. But, I mean, to me, the big mystery is dark matter and dark energy. Those are overwhelmingly the biggest parts of the universe, and we don't understand them at all. It's quite amazing how little we understand, but we are, of course, observing dark matter in great detail, and we're every year learning more and more about it, and we will come to observe dark energy, no doubt, as time goes on. But still, I would say those are, to me, the two most outstanding mysteries.
So, I wanted to. One of the most interesting, I think, qualities of your work is that you are very willing and I think very excited to take on controversial viewpoints. Is that a fair assessment? Do you think?
Oh yes.
So you have a chapter on climate change in this book, and you point out that the work, I think correctly, that the work of science is never finished. There should never be an orthodoxy that can't be challenged. You describe proponents of global warming and environmentalism generally as being part of a religion with, and I liked this quote, even though I don't entirely agree with it, the path of righteousness is to live as frugally as possible. And tomorrow happens to be Earth Day. And, you know, given that we've got days sort of just celebrating this, I think there's a point taken there. But here's my question for you. So you put the idea forth that we should certainly be skeptical, that we should be willing to challenge science, but also there comes the time when further study is, in a sense, a rhetorical device, meant to postpone action potentially indefinitely. And, you know, much of the urgency from the environmental movement is intended to counter claims that might be funded by the energy industry, for example. So at what point should society and the scientific community make the equivalent of Pascal's wager? At what point do we collectively accept that there's enough information to act?
Yeah, that's of course a question of judgment, and I happen to have worked at Oak Ridge. That's where I learned what I know about climate. And at Oak Ridge, that's the national laboratory, which in those days was run by Alvin Weinberg. And they had there a group of, it was called, I think, the Center for Energy Analysis or something. Anyway, it was a group of people who were concerned with energy on a large scale. And it included experts on forests, experts on vegetation, expert on soil and on the microbes that live in soil. So it was heavily into the ecology. There was also people who understood a bit about meteorology, about climate, and so it was balanced. And I think we understood that all these things have to be taken as part of the big picture, and it only makes sense to start making recommendations to the government about policy. If you look at all points of view, and especially the ecological point of view, the ecology is really what it's all about. And the climate is, to my mind, a minor issue as compared with the ecology. And I think that's the basic difference between me and the majority. It's not a question so much of the facts, it's a question of the emphasis, that I would put far more emphasis on the biological aspects and much less on fluid dynamics. And if you look at the climate, what's called climate science, it's actually just fluid dynamics, that's all it is. And so they do big computer models of the atmosphere and the ocean, which are all just fluid dynamics, but they don't have much else. Whereas the real world is enormously more complicated. The real world doesn't come into their models at all, really. And so it's somehow or other this fluid dynamics community has become dominant. It has a tremendous political punch. And that's why I disagree with it. I think the emphasis is wrong. I believe the ecology should come first.
Interesting. So one of the, it's just I'm thinking about how much you can trust any particular scientific model. One of the things I thought was very interesting is William Nordhaus's Question of Balance, on which your chapter on global warming and climate change is primarily based, relies really heavily on economic simulations. And I would make the argument that there's a lot of black box computing going on there, that we don't really know what goes on inside the black box. Can we, if we can't understand the atmosphere moving into a century into the future, can we understand human phenomena, human behavior a century into the future?
Of course not, but of course I wouldn't say that necessarily is what is really the practical question. I mean, the practical question is, do we actually know whether we're doing more harm than good when we take some action, for example, to try to limit emissions of carbon dioxide into the atmosphere? Do we understand the effects on the ecology well enough to know whether we're doing good or doing harm? That, to me, is the question which I don't know the answer to, and I don't think anybody else knows the answer either.
So I'm just curious. So, this is a specific question of the environment. Do you feel like there are other areas where the scientific orthodoxy or any of the orthodoxy is just way off base?
So, well, I don't think of anything at this moment. Undoubtedly, there are a lot. I mean, but I would say, most of the time, it's we're dealing with political questions rather than scientific questions.
So I want to move to a slightly lighter topic, and I know you're not crazy about the I've read that you're not crazy about the naming convention, but one of your major legacies, though perhaps you didn't intend it this way, is in the realm of science fiction. So in the 1960s, you proposed what's now known to others as a Dyson sphere, which I've heard, please correct me if I'm wrong, that you're not crazy about the naming convention, but it was proposed, you proposed it as a possible signature for super civilizations. So if we're looking out there for intelligent life, the construction is basically a giant sphere at about the Earth's distance from the sun around a star, and then you increase your livable area by quadrillions. And in principle, all of the energy going in re-radiates, and we could look for big infrared signatures as a way of looking for super civilizations. But I'm wondering more generally, you can comment on that, of course, but if you could comment on the interface between science and scientific proposals and science fiction, and potentially how they're used or misused in popular culture.
Yes, I love science fiction, and I wrote a piece for The Week magazine just now about books, and there are 4 science fiction books which I was recommending, which all of them are concerned with religion in one way or another. And I think that's what is important about science fiction, is that it's about human people, it's about emotions, about real problems of human life. It's not about science. And it really doesn't matter whether the science is right or wrong. The important thing is whether the people are well drawn and have serious, presents a serious point of view. And anyhow, the 4 books I was recommending were all of them written by friends of mine. And there are 2 which are written by Octavia Butler, which are the parable of the parable of the sower and the parable of the talent. And then there was 2 written, which are the sparrow and children of God. And they're all, I think, wonderful stories about people who are primarily concerned with religion rather than with science. And I think that's the truth. I mean, religion goes far deeper into our history. It goes far deeper into our way of thinking than science. And so I'm an advocate of science fiction, really, not because it has anything to contribute to science, but because it has a lot to contribute to wisdom. And
so, that was actually going to be a follow-up. So, in your discussion of the Tsiolkovsky version of Dreams of Earth and Sky, he starts off with discussions of sort of the science of propulsion and rocketry, and then talks about aliens and how small asteroids are preferable to large planets and things like that. You know, in the sense that, is there a sense in which science fiction speculation can inform real science, or do you think it's only a one-way exchange of information?
No, of course it goes both ways, but certainly not so. It doesn't certainly contribute in a major way to science. It might be just sort of worth remarking about this Tsiolkovsky story. I mean, the whole point is that if you really want to live in space, which these aliens do, that you have to be different from humans. There's no way humans could be happy wandering around on Mars. We have to change biologically. We have to adapt to wherever we're living, rather than trying to adapt the surroundings to us. And there's no future for humans living in little tin cans on Mars. That's not going to be attractive to anybody. We have to be out there in the open. We have to have some way of surviving in inhospitable environments. And the way to do it, of course, is by evolution.
So, you know, looping back to this discussion of the speed of evolution, and thinking perhaps about our future in space, what sort of timescale do you think before we really get out there and colonize space?
Well, I would say it is not so much thinking of we. I'm thinking of life as a whole. I mean, it's not. Human beings are never going to do very well by themselves. But as part of a spreading of life, we can do very well. But you have to think of life spreading in the universe, same way it's spread here from the ocean to the land, and it takes time. It takes clever inventions. The creatures that came out of the ocean onto the land had to invent lungs, and when we go into space, we have to invent something equivalent, so that we can use sunlight as our source of energy to keep alive. And so we have to essentially to transform ourselves, as Tsiolkovsky imagined, into what he calls animal plants. Animal plants are creatures which are both animals and plants, so they have brains and muscles to move around like animals. They also have leaves and branches to take nourishment from the sun. So that's the sort of way you have to think about the future in space.
This is during the century of biology. We'll get started. Actually, which brings to mind one other question related to all of that. I mean, we're talking about colonizing space and moving out into space, and perhaps changing our physical form or that of our descendants. You're, in a very significant way, and I think you exemplify this, we're breaking down the barriers between discipline. I will say, from inside academia, interdisciplinary work is one of the big catchphrases of the day. And, you know, I'm very curious as to whether you see a real future in sort of pure disciplines, or whether the expectation sort of for making future progress in science and in elsewhere is going to come primarily from this interdisciplinary approach, one that, as I say, you have sort of exemplified in your thinking.
Well, you need both, of course, and I would say it's not so different if you take music to compare with science. That, I mean, there are many different kinds of musicians, some who are just enormously skilled at one instrument, and that's their life, to acquire and practice this skill, to play the violin better than anybody else, or the trombone, as the case may be. But then there are other kinds of musicians who enjoy all sorts of activities. They do a bit of conducting, a bit of composing, a bit of teaching, a bit of performing, and are essentially equally good at anything. And of course there have been plenty of those too. Somebody like Bach or Handel were very much of that kind. They were not specialized. They could do everything and did everything well. But, so we certainly need both kinds, and it's a question of taste which you happen to prefer.
Fair enough. So I think we have time for a couple more questions. So I guess my big question for you, I see two big themes in your book, and I was wondering if you could sort of comment on them collectively. I mean, one is sort of the role of challenging orthodoxy, and the other seems to me, and you know, you can correct me if you feel I'm off base, sort of the role of the thinker in society. I mean, there's a lot of your essays are based on sort of great thinkers, great thoughts. I was wondering how you see those two intertwining, basically.
Yeah, well, I see myself much more as just practicing my skill as a writer. And the subject matter is given to me by the magazine I write for, and
you don't choose your own?
I don't know. I mean, I love to work for the New York Review of Books because I don't have to suggest books to them. They send me books, and all I do is to say yes or no, and I find that much more congenial. And in fact, the books that they send tend to just to have that emphasis on science as a part of the public life, as scientists, as public figures, and as thinkers who influence the public. So that is not so much my choice as theirs, but anyway, it suits me very well.
So you say yes or say no. How do you decide if there's something that you just, as ambitious as you are, as much of an eclectic thinker that you just can't tackle this subject? Has there been anything that was sort of might have been your sort of dream topic? It just didn't feel like you were up to the task?
No, that's not the problem.
Understood.
No, the ones I say no to are generally just books which I consider bad.
So if you...
There's no joy in writing a review just to say, don't read this book.
And on that note, let's thank Professor Dyson. There are microphones going around. We will now open up the discussion. Wait till you have a microphone to ask your question, and wait till I call on you. I have apparently enormous power here. So if you could go to the front row there. And who else is a microphone bearer? Okay. Okay, let's stand on back there.
Thank you for coming and sharing your wit and wisdom with us. You raised as two great remaining mysteries, dark holes and dark energy. from your vantage, what is the best current speculation or understanding, or what would you expect we will ultimately find that they are?
Well, the whole point is that that is an unanswerable question, that we have absolutely not the faintest idea what they are, but we can find out, and that's what makes it exciting. There are two very different things, dark matter and dark energy, because dark matter is observable in considerable detail. So we do have some real facts there as to which may in fact be a clue to what it is. Whereas with dark energy we are much further away. But in both cases I would say it makes no point at all to guess at the moment.
Interesting.
In the last century, nuclear weapons, the dangers of that sort of thing. We're looking in the century of biology to all sorts of creating types of life that could take on a life of their own, perhaps out of control. Nanorobots. What about the responsibility of scientists to consider the consequences of what they discover?
Well, I must say there is a big difference here between the way the physicists behaved and the way the biologists behaved. That the physicists, of course, rushed into building bombs without any public discussion. They immediately, as soon as fission was discovered, immediately started thinking about how to build bombs and went ahead and did that in a, I would say, a totally irresponsible way. The biologists, in contrast, have been very cautious. Just a few weeks ago, they had a conference in Napa in California to impose a moratorium on certain types of manipulation of human germ cells until the consequences can be worked out. Nobody should do such experiments. And that was generally agreed. I mean, the biology has worked that way. That happened 40 years ago with the conference in Asilomar when recombinant DNA was first discovered. They decided at Asilomar in the same fashion to have a moratorium which lasted for about a year while consequences were considered. And in the end, they agreed on guidelines which have worked very well for the last 40 years, so that the dangers to public health, in fact, have been avoided. And I would say the biologists have shown us how to do it, and we should respect that and try to do as well with physics as we did with biology.
The question.
Certainly the biological dangers are real, and the biologists are well aware of that.
Mr. Dyson, so whether cultural evolution or biological evolution is holding sway today, looking around the globe, does anything give you optimism for the future of the human species?
Yeah.
Oh, yes, of course. I mean, I had the great good luck to grow up in the 1930s when all the problems that we're looking at today were far worse. I mean, it was, in the 1930s, England was far more polluted than it is now, and unemployment was far worse than it is now. The economic depression was far worse. Hitler was on the horizon. World War II was coming. That was far worse than anything we are contemplating at the moment. So I would say, having survived the 30s, I couldn't help being an optimist.
I'm associated with a theater company here in Philadelphia that produced QED about Richard Feynman. And this fall we're going to produce a play about Rosalind Franklin. I would love to hear your advice on who are another 2 or 3 scientists who, both by temperament and the drama of their scientific quest, deserve that kind of treatment.
Yeah, well, I think of Lisa Meitner, of course, who I don't know. I never met her, so I don't know what she was like. But I read a biography of Planck, which has a lot of information about her, and she was, of course, a very close friend of Planck all his life, and. So she would probably be number one on my list. I don't know why one thinks of women always, because they generally are, somehow they have some kind of human understanding which we males lack. And
Thank you very much for being here. I first saw you in Berkeley, and that was 40 years ago, so I have to congratulate you on your persistence. Einstein famously complained that quantum mechanics must be incomplete because of the unexpected correlations, let's say, over great distances. And even the collapse of the wave function is inherently superluminal, I think. Do you think that anything any progress has been made? Do you still feel do you agree with Einstein that it's incomplete for that reason?
No, but no, quantum mechanics really works amazingly well, and it of course, the problem with quantum mechanics is it takes mathematics to explain it, and you can't really explain it in words. Our language is entirely concerned with the classical level of things we can see and touch, and quantum mechanics is different. So it has this mathematical language which is amazingly beautiful and amazing. I would say amazingly complete, and it's of all the parts of science in a way. It's the most perfect. So I would say the opposite of Feynman and opposite of what Einstein said. If anything, it's the existence of the classical world which maybe is not completely understood.
Yeah, back there.
Once or twice in the course of the last 45 minutes or so, the word religion has been mentioned, and I'm wondering where you come out with regard to how religion might factor into the things that you've been working with, or spirituality, or the sense of a purpose that drives the universe.
Yeah, well, I take a separation of science from religion as to me absolute. I mean, that to me science is just a bunch of tools which happens to work spectacularly well for dealing with certain kinds of problems, but it is just a set of tools. Religion is totally different. Religion is a way of life, or a community, a great literature, architecture, music, all kinds of other things. So I don't think it has anything to do with science.
This one first.
Okay. First off, thank you. As a PhD candidate in physics, thank you very much for your work improving upper hanger wrong. It helps quite a lot when we were doing particle physics in the fall. But my question comes more of just an entry-level scientist to ask someone of such diverse talents. What's the biggest thing that you've learned over your career that kind of keeps you going in looking at new different things?
Well, mostly it is just talking to people, and I've always been a follower rather than a leader, and so I talk to people, and when they doing something exciting, then I get involved, and that's my way of working. I don't think I've ever started anything by myself.
Yeah.
And that's something that is beautiful about science. It is a collaborative life. It's very different from pure mathematics in that way. I mean, pure mathematicians really seem to work much more alone. But in physics and in biology, we work almost always together in groups. And to me, that's much more satisfying.
My question's on a similar line, actually. I'll be entering graduate school in the summer. And I greatly admire your generation of physicists and look up to them. But the question I'd like to ask is to think about young scientists entering their careers today and what has changed, or how my career as a scientist over the next so many years might be different from the career that you've taken.
Yeah, well, the obvious thing that has changed, of course, is computers. That the tools that are available are very largely based on computing. And that's true in all branches of science, in biology or in climate science or in particle physics or in astronomy. Everybody uses big data. Everybody uses essentially the same tools to handle data. So the consequence is it's much easier today to switch from one field to another than it was 50 years ago. So I think that's a big plus. So if you're a young scientist today, you don't really have to decide in advance which branch you're going to do. If you're well equipped with computing and a certain amount of skills in writing and reading, that's good enough. You can do almost anything. And so you can decide to be a neurobiologist, and then you don't do very well, you can switch to climatology.
Other questions? Over there?
But I don't say you should go to Wall Street.
Mr. Dyson, what was John von Neumann really like, and what obtained in the last 50 years that would have shocked him the most, do you think?
Johnny von Neumann, of course, he was a very cheerful character, and I didn't know him personally so much. I just listened to him talk, and he was running the computer project in Princeton when I came there. This was the first programmable computer with its own stored programs. So it was a pioneer venture, and it worked extremely well. And so the main thing that would have surprised him was the fact that computers got smaller and smaller as they got more powerful. He always thought of them as being big, monstrous, very expensive, and belonging to big corporations. In fact, of course, they became cheaper and smaller and more user-friendly, ended up as toys for 3-year-olds. He really would have been surprised if he'd known that. And
it's right there in the middle.
Along the lines of some of the other questions, science is increasingly being funded for big science projects, and like the discovering the genome or the boson particle. Huge teams of researchers. Do you think that's going to affect how science is done, and there'll be less standouts like Einstein?
Well, the public, of course, has a distorted view, because the big, expensive projects always are the ones that get attention from the media, and it's not accidental. If you have a big, expensive project, you need attention from the media to survive. So if you take, for example, the LHC, the Large Hadron Collider in Geneva, it's enormously hyped. And they have to hype it because it's so expensive. The same, of course, was true of the Hubble telescope and various other big projects. I mean, they're doing good science, but they're not as great as they pretend. And if you look at the real world, there are lots of small projects going on that people don't hear about. That's still true, and it's true in all branches of science. In physics in particular, there's a lot of very, very good physics going on quite small scales. But of course, you don't hear about it. And I hope that'll remain so. And I think the balance is certainly too far in the direction of big projects. The big projects tend to get the money more easily. They get more votes in Congress because they essentially are welfare programs for the industry. But in spite of that, the small science is still surviving quite well.
If we can get in the interior over there. Yeah.
Professor Dyson, it's a pleasure having you here. My question is simple. Did you ever meet Alan Turing and Claude Shannon by any chance?
No. Too bad. Neither of them, in fact.
Professor Dyson will be accepting all yes-no answers. We can get another one back there.
I was wondering if you would comment to what extent you think human history is an extension of the biological evolutionary process, and that societies are like species. They come and go depending upon their environments.
Yes, I think so. And of course, I read Jared Diamond and various other people who put forward this point of view of looking at the history of evolution leading up to humanity as part of the same picture. And I think it is, largely speaking, true. Many of our characteristics can be understood much better as a consequence of our evolution, of the kind of creatures we evolved from. One of the things that is most characteristic of evolution, which is not, I think, this was stressed mostly by Ursula Goodenough, who's a writer who's not well known. I think one of the most insightful biologists. I mean, Ursula Goodenough looked at different genomes all over the biology, right all the way back to seaweeds and up to chimpanzees and humans. And she found there's two kinds of genes which everywhere are very rapidly mutating in all species. That was quite surprising. I mean, we know there's one kind, that's the immune system. The immune system has to mutate very fast so that your immune reaction can quickly be mounted against an alien invader, so that the genes actually have to change in order to adapt to whatever it is that's invading the body. So the immune system is rapidly mutating. But in addition to that, she found there's another set of genes that mutate rapidly, and that is mating systems. Mating systems, that came as a surprise. Why should mating systems change rapidly? And the answer is, and I think Ursula understood that, that that's nature's way of driving evolution. That in order to evolve to any great extent, you have to have new species. And the only way you can have new species is to change your mating system. So you have two creatures who are different from the others who like to mate together. So their chance of survival is actually very small, since they're so unlike the majority. But if they do survive, they start a new species. So that's nature's way of driving evolution. And I think that's the way we evolved too. And if you look at human evolution in the last 5 million years, there have been a huge number of species. We're not just descended from one species, which was like the chimpanzees. There's been 30 or 40 species in the last 5 million years. We are the one that survived. And that's probably going to be true in the future. So look forward to rapid evolution, whether we drive it ourselves or not.
Over there, about halfway down.
Hi. I was kind of going back to the idea of big science and the problems that can be associated with that. There have been a lot of critiques of like potential problems that can fall into, specifically thinking of Weinberg. What do you think the best way to kind of go at avoiding those problems for big science would be? Do you think it should come from a policymaker standpoint, project managers, individual researchers? Since there are so many projects now that arguments have been made need a big science approach to be tackled appropriately.
Yeah, well, I have seen this going on in the domain of astronomy, where they have an institution called a decadal study. Every 10 years, astronomers come together and decide on what they'd like to have for the next 10 years. So they have big plans, of course, for new kinds of telescopes, space missions, and also a lot of small instruments on the ground, which are much cheaper. And the problem is to establish the priorities so that the big and the small don't compete with each other. If the big and the small compete in the same funding committee, of course the big projects always get more votes. Just that biases the system in the direction of big projects. So you have to have a division of all the projects into big, medium, and small, first of all. So you have, say, decide on 1/3 small, 1/3 medium, 1/3 big. And then you make the political choices then only inside the three divisions. And that has worked reasonably well. I mean, that's the way the astronomers do it. I think it could be applied to other parts of science in the same fashion. Doesn't always work because, unfortunately, the big projects very often get too much support. They go behind the decadal recommendations and if they get enough votes in Congress, and of course the thing gets supported. But anyway, that's the way to do it, is to arrange it so that the fraction of the funding going to small projects is fixed first, and then you make the choices.
And we have time for one more question, so let's make it a good one. Okay. Right back there.
Thank you very much. I really enjoyed your presentation. I've always enjoyed your comments in New York Review of Books and many other occasions. I think it would not be a complete discussion if we didn't introduce Socrates into the discussion. And the great ancient Greek philosopher in 399 BC had asked a question of Plato, which was referred to in Phaedo. And that question was, how does one person and one person become two persons? I do not understand. By their mere juxtaposition, whereas they were separately one person and one person each, how they become two, I do not understand. Has that question been answered?
I don't know. I mean, to me, it sounds more like a question of words than a question of substance.
And on the note of criticizing Plato, thank you very much for a very enlightening discussion.
Book TV is on Twitter and Facebook.